should update because there might be security holes if you, yeah, then this works nice. Yes, so I got a nice introduction to myself. So now I will start presenting the work that my students did in collaboration with me, Ole Kristoffer and Morten. So the stars of this work is Didrik and Andreas, and quickly after their master thesis, we hired them to AI experts in Norway. So because of their very nice work. So here we have a table with some contents, basic standard for our presentation. So I'll just jump right in. We have these neural networks. Everyone have heard of them. They are quite complex, and the last decade have been even more complex. And when I did my PhD, I worked on deep reinforcement learning, specifically trying to solve this StarCraft 2. And what happened was essentially we started using deep neural networks with a few million parameters. So this ended up being my office. Clearly, to succeed, you needed GPUs, a lot of GPUs. So I guess everyone knows that this is a Bitcoin farm, not an actual rig for science, but basically it shows the same principle. So today, with deep neural networks, this is nothing. So you can't really do anything with this nice rig. Now you need this. So these are the H100. So and everyone wants these for training their deep learning models. So again, things starting to let's say scale up, and the last decade has been a race towards scaling things up in neural networks. And when you scale up, you can solve games like StarCraft. I couldn't because I didn't have the H100s, but DeepMind managed to do it. And after they solved AlphaStar and a few other high-level games, kind of all of the research in game AI in a way disappeared, or at least the tempo that we saw during my PhD. It was suddenly it went from full speed to very little speed, and I wondered why. Suddenly we got this ChatGPT, and now I realized, okay, why did DeepMind want to solve all of these games? Yes, it was to solve this PPO part, the reinforcement with human feedback in ChatGPT and large language models. So there we basically have it, the PPO, proximal policy optimization algorithm, that they solved a lot of games with. Now they don't care about games anymore. Now it's only ChatGPT. And we all know the size of ChatGPT, billions, trillions of parameters in total. Also during my work, we try to use kind of interpretable and explainable methods to see what our neural networks saw. And that works fine if you have small networks, simple networks. But when you get these very large models, it quickly becomes difficult to understand what it's actually doing. So that is kind of the motivation. Okay, now we are just scaled up the last decade. Now it's getting out of hand. We can't really understand what these models are doing. So now let's try to go down into complexity, and that's where Tsetlin machine comes in. Yes. So I will start with a brief introduction to reinforcement learning. I will skip the Tsetlin machine one because I guess everyone has an idea of what that is. But reinforcement learning, essentially, you have this agent that wants to interact with an environment. So it's a feedback loop. So when you have made this action, the environment will give you an observation of its state. Maybe it's full state or maybe part of it, the state. But nevertheless, when you get the state, you also have some reward that you should get. And that is often a user defined. So, and that is in reinforcement learning, for example, for ChatGPT, they defined, they used supervised methods to create these reward functions by hand. And then in this environment, they try to optimize the agent so that it works optimally for that environment. We have different algorithms. First, for example, the value estimation algorithms, Q-learning. So value estimation is essentially how good it is to be in a particular state in a game. So if people don't know what a state is, it's essentially, okay, if we imagine me as an environment, so now I'm in the standstill state. Now I'm in the arm left out state, and so on. And then you try to measure how good it was to be in the arm left out state, for example. And the Q function, basically, or the Q values, those try to measure how good a particular action was in that observation or that state. So that's a way of indirectly doing decision making. You also have policy gradients, which are a more direct way of doing it. So you take in a state and you get out an action based on your policy. So often we call this a direct policy search, and that is the basis of this paper. You can also combine these to actor-critic, where you have one part that estimates the values, and one that estimates or kind of do the action directly. So that's the actor. Yes. So now it's where Tsetlin machine comes into play, and the part that we kind of focus on is the agent. So we want to have a Tsetlin machine that acts as an agent, and we want it to be direct policy search based, so that we put in a state and we get out an action without any fuss. So I try to do it as close as possible to the traditional reinforcement learning methods. Yes. So in this work, we had two environments, quite simple environments, but nevertheless advanced, where we are currently in Tsetlin machine research. So cartball is one. You have four on the right. You have four state variables. Those are continuous. So here we kind of already hit a problem with the Tsetlin machine, because we need to have some binary form of these data. So that's one challenge with that. And even also with the Pong, that one is actually more convenient, because this is an Atari game and you can just use the RAM directly. So that is convenient in this case. Yes, so now I kind of spoiled this slide, but yes, we used the RAM representation for Pong, just using the bits directly. We defined a reward function where the player or our agent would get a plus point if it scores, and a negative point if the opponent scores. So that's a quite intuitive reward function. For cartball, then we use this standard, I call it the standard Booleanization method that we use very often in Tsetlin machine. So essentially what you do, you take your number and then you threshold it. So you ask, is this number larger than 5? If the answer is yes, then you set a 1. Is this number larger than 10? If it's yes, then you set a 1. Is this number larger than 15? If the answer is no, you set 0. Then now I made a 3-bit representation of that number, essentially, or that state, for example. Yes. So in our TMU repository, the one that Ole Christopher works on, there we have some of these pre-processing features, and we also add those, that when we come up with new ideas, we also add them there. Yes, very long explanation of that. So, but anyways, the reward function for cartball, we had to change a bit from the default that we get in the OpenAI gym. We used +1 if the pole is correctly balanced. So basically, as you saw in this image, when the pole is balanced, then we get a +1. 0 if it's falling, so it's starting to fall, lost its balance, and -1 when it reaches the terminal state. That is essentially when the pole has fallen into a angle, the specified angle, then it's a terminal state. So one trick that we did was to first we sampled these environments with just random actions, and we saved those into just NumPy files. So we saved the sample so that we could do some pre-training first. Yes, and now we had some data that we could pre-train on. And now we needed to find out the hyperparameter searching. So we used, I think we used Optuna for this. And we set some crazy thresholds from minimum to maximum on what we wanted to test. And then we just set it on play, and we found some good hyperparameters that way. And clearly here we should have had some more educated starting points, because this is quite large state or a search space, but we have some compute, so it worked out well in the end. Yes. So yes, so this research was, in a large way, because we had not really no idea how to get this working in the start. So first way we wanted to test if this if Tsetlin machine were able to learn at all. So can it imitate a good policy or a good reinforcement learning algorithm? So we call that the imitation learning experiment. So what we did, we downloaded a pre-trained proximal policy optimization, so basically policy gradients algorithm, and we tried to make Tsetlin machine imitate this. And it worked well. So yeah, I had to ask my students what's different, the difference between PPO demo and normal PPO, but it was two different pre-trained models that we tried to follow. So one is more fine-tuned than the other on this problem. Yes, so this was CARTPOL. So in addition to that, we also tried, because we can also define the optimal policy just with math in CARTPOL. So we also use that as a policy. And what we ended up with, I should have made the, there we go. So these are the results that we ended up with. Yes, I will check the next slide so that I don't lie. Yeah, I think these are the results, yes, that we ended up with when we used the imitation learning, the 380. So the top score is 500. Yes. Good. Yes. So also other, yes. So here are the other results with the demo. If we imitated the demo PPO and the normal PPO, so we got a decent result, but we did not converge like to the top. But according to like the specifications of CARTPOL, these, at least the demo PPO was, they considered it solved. But I would like to see it on the top like this, at least a graph that goes up and we converge fully. But that we didn't manage to do with the imitation learning, trial experiment. Yes, so okay, we got some results. So a bit promise. We could see that we're now learning something. We can get it to get scores below above 50, for example. So often when you have a policy that doesn't work, then it's about 50 or less in average reward. So now we got 300. That means it's learning. It's capable of doing good in this environment. Yeah, we could also see that it was very unstable. So you had a standard deviation on 161. So that means it's not stable. It varies a lot in the results, but it can learn. So the next experiment, now that we knew that it has the capability of learning, we wanted to try like going straight into the problem and doing model-free policy search. So what that means, okay, so in reinforcement learning, you have model-based, where you create this, you have a model of the environment that you try to solve. And in model-free, you just skip that part and you do exploration, exploitation instead, directly in the environment. So in the second experiment, we had three approaches. One, just following the epsilon greedy exploration exploitation scheme. That's basically the same as we would do in normal reinforcement learning. Yeah, and also double TM. So I guess those that have worked with reinforcement learning have heard of double Q learning. For example, you have two policies, one that do the inference and one that trains, and then you copy the weights on a regular basis. And finally, we have the batching approach. That's one. That one is a new one. And it's basically I won't spoil, but that's the new addition to reinforcement learning with Tsetlin machine. Yes. So now I told you that already, and what we got eventually was so for the epsilon greedy and double Tsetlin machine, as I told you, if you get low scores like this, it doesn't work. So here we got very bad scores below 50. That means it's not learning anything. You could just as well just have a random policy and you would get the same accuracy. So instead, we jumped onto some new ways of doing things, what we call the batching approach. So here, this is quite simple. We have a buffer and we sample all of the positive. So those states that gives positive reward, we store that in a buffer. And if that buffer reach a certain amount of samples, so let's say we started with saying, okay, we need to have 3 samples in a row that are positive, then we will train on that batch of samples. So in this case here, we started with a requirement of buffer size 3, and here we got a positive sample, and then we got a negative sample. In that case, we clear the buffer and try again. And since we also use epsilon greedy in this method, you also get quite a lot of randomness, and eventually you will hit 3 in a row. So for the next iteration, we did it again, and yes, we got 3 samples in the buffer, and then we train on those samples with the Tsetlin machine. And additionally, we increase the requirement for training. So now we need 4 samples. So then we do it again. Okay, positive, 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 positive. Okay, we train again. We set the requirement to 5. And we do that up to a point, for example, buffer size 32 or something like that. And then, and it goes like this. So also one approach that we did is if you then eventually if you fail, then you might also decrease the buffer size so that you go down and kind of lower the requirement. So yeah, so that's the general idea of this method. But we can see that this general idea of the method, it worked quite well. So now we have an average reward of 574 out of 500, also quite low standard deviation. So that means it's actually balancing the pole, and it's also balancing it quite stably. And that's good. Yes, so then we can, now we solved the problem. And according to at least the requirements, this is solved. But still, I would like to actually go to top 500 and stay there. Yes. So these are fancy graphs that nobody can see what says because they are too small. But essentially, that shows my table. These also shows my table. Very nice graphs. Yes. So now for the final challenge, Pong. So Pong is also a difficult problem, comparably to the Cartball one. It's much more difficult, and especially when we start using the RAM directly, then you're talking about a big jump in state complexity at least. So here we used the same approach, the same approach with multi-batching that we called it. And here you can also see some graphs a bit. And what I can say is that we did not solve the problem. Minus 20 means that the opponent scored 20 times. If we get plus 20, then you have then we have won. So what we can see here is that So I like to read this as okay, it didn't work at all, but it learned something because you can see that it's gradually getting more and more wins in a way. So that to me indicates that it can solve this because there's no way that you get 20 points with just randomness. That is way too many states and too many actions to achieve. You cannot win on randomly. So that's at least my take on this. So yes, it's capable, but no, the hyperparameters needs tuning, and we need to figure out a way of doing this a bit more stable. But we have shown the potential here that it's possible, I think. Yes, and the same goes for these results. It's the same. We can see that it's able to do some progress up to 20 to scoring 20 in Pong, and that means it has the capability, but it's not able to achieve it. So now I spoiled future work. But as I said, one does not simply win Pong randomly. So I think that is at least a lesson from these results that okay, I think it's possible. Yes, for the road ahead. That will be for the road ahead. So the conclusion here is that out of all of these tested approaches, the batching one, the special batching one, is the one that works best. And we saw that it can learn by imitation, but actually it's not as good as the model-free version when we use the batching method. So yes, so we can also learn from scratch, right? The model-free one, and it's able to solve Cartball, and that's actually a challenge that we haven't solved before. So I think that is a great achievement for my students, at least. Also a good achievement for me, because now I can work on Pong. So yes, and we saw the potential of beating Pong, but here we need more work. So yes, future work is to study why this epsilon greedy does not work, because the end goal would be that we could train Tsetlin machine exactly the same way as we do in normal model-free reinforcement learning. So basically, you have this epsilon greedy exploration, exploitation, and then you train just directly without this batching method. So that's one approach for future work. And also, why does the batching work so well? That's also a question. Why does this little tweaking work so well comparably to just epsilon greedy? And also investigate what is it that makes the Tsetlin machine policy collapse in Pong. So why are it able to solve, or at least win, with 20 points one game and then completely fail the next? So what is it that makes is it changing the policy too much? And if so, how can we reduce these changes? That's actually a bit like we saw with policy gradients and proximal policy optimization. So in policy gradients, they had large updates per sample, and to fix the instabilities, yes, we then limit updates. That was the fix. So here maybe we need to do the same in a way. Yes, and finally, how can we actually? So we need to also study: can we find new schemes like this batching scheme to support this direct policy search better? Yes. So I think that is it. Thanks for listening. So yes. Yes.
So, any questions from our audience? Yeah, Lay.
I just wonder the scalability of the approach for a bit bigger problem. Could you please comment?
Yes. So as we could see, for Cartball, it worked quite well, and if we use it on Pong, which are scalably much larger, then we can see that it's not working. So I think there's some scalability issues, but we don't know what is exactly making the policy explode or collapse, because so that's kind of the future work. Why is it working so well now on Cartball, and what makes it difficult to work on Pong? The complexities there's so much complexity difference, and now is the question: what exactly is making it collapse? That we don't know. No idea. Yes. Suggestions? Yes.
For me. Yes, please.
Yeah. Hi. Thank you. Just you were talking a little bit about the hyperparameters that you used before you showed us some of the results for Cartball. And I'm just wondering, did you do like a similar kind of hyperparameter search when you moved onto doing Pong? So specifically, I'm thinking about things like with the epsilon greedy policy and that sort of thing. Like, is it potentially that the epsilon greedy policy you're using isn't giving it? It isn't allowing the model to explore the search space enough in order to learn an optimal policy before it moves on to exploitation.
Okay, so so when we ran the experiments, we used the same search space for both environments. So we didn't fix these when we tried the new environment. For the epsilon greedy one, I think we used we started at 90%, like something like that, with exploration, and then gradually annealed over a few. I can't actually remember that. I should have. We also had that in these hyperparameters, how fast it should reduce, and I think we ended up with reducing until 10%. So we did 10% exploration eventually at the end. So that was part of the search space, I think, as well, but I didn't have space. Yes, did that answer it?
So I'm thinking like in terms of the decay.
Yes.
Did you use like the same decay with the cart pole, or did you use something that maybe allowed it to search use exploration a bit more before it sort of transitioned towards exploitation?
Good questions. I think it was fixed. I think we set it to something like 100K steps or something like that, and just linearly decayed for both actually. Yeah. So, but I think we changed the starting point for how much you should. But very good. Maybe we should check, because obviously more complex problem maybe needs a lot of more steps. So that's good input. That will definitely test. Yes.
No worries. Thank you.
Thanks.
Thank you very much. Very nice question. That's good response. Right. You didn't change the number of states as a parameter. So did you fix it first? And second, why didn't you try to change it?
The number of
states of the automaton.
Yes.
So what was the number of states here, and why didn't you try to change it? It may have some impact.
Good question. I have no idea why we didn't change it. So yes, I actually don't know. That I would have to check so I just yes. Good point. I'm not sure.
Okay.
that I will check, and if not, I think that should be in the hyperparameter search. I know that we had a lot of parameters, but we tried to limit the search space. So the question is if they gave me the full list, the students, or if it was excluded. Mm-hmm. But clearly it should be. Maybe if I recollect correctly, I think we had we said 16, 32, and 64 or something like that for that we tested in this search space. But I think that was I think we had some, but we did not have an exhaustive search on that.
It may have impact. Yeah. Right. Yes, please. Yeah.
Other than gaming, what are the potential applications where your work will be useful?
In gaming, yes.
Other than gaming, sir. Other than gaming, what are the other applications?
What other? Yes. So smartwatches, for example, small IoT devices. A lot of IoT devices needs to do decisions. Now we need to send the traffic to some central unit somewhere. But imagine if we could have the world with all of these small Tsetlin machine chips, and that they could do decision making live. So I think that is the goal, and I think it's much like the like DeepMind did with solving games. Okay, we solve games, then we go to LLMs instead. Here but they go up. We need to go down to the small part of the world. I think that is the best application for Tsetlin machine is the IoT space, and I think we have the benefit there because the IoT space is growing extremely, like the billions, 50 billions of devices. I mean, it's enormous. So imagine having this little chip on all of them.
But how will you do something like this? How will you do something like reinforcement learning on small chip? That's because reinforcement learning takes a lot of resources, right? So you're saying you will do this with smartwatch.
Yes. So one example would be, let's say if you have a problem that needs some learning, then you could use a Tsetlin machine decision-making chip to tune parameters, for example. One way. So that's the way that we use PPO in ChatGPT. We fine-tune the model, and the same we could do with this type of application. We could start with some nice parameters that we think are best, and then we could fine-tune those with informed decision support. I guess it's a good way of thinking of it.
So in some sense, Tsetlin machine acts as a second order type of learning here compared to some other parameters. So basically we learn hyperparameters rather than
that would be one application, I think. But yeah, for example, I had the idea that maybe we could use this in cars, for example, but then maybe I think cars are very big, so you have space for large hardware and you have batteries that so we don't really care that much maybe of power. But I think if you would go in even smaller things that needs to be compressed to small spaces, IoT, for example, then I think it's many good applications in medicine, in personal health, and things like that. Hope that answer it in a decent way.
Right. Well, thank you very much, Per-Arne.
Yes.
It was a very nice talk. Yeah, very thought-provoking.